Dear participants and professors, the International Second Technology in Medicine Symposium continues. I'm Gülbin Rana Dilek, a third-year medical student and the president of Ankara University Neuroscience Community, and I will be moderating this session. We would like to remind you that our attendance form will open at the beginning of the presentation and close at the end of the session. And then we will move on to the Q&A part. The president of
you can ask your questions by filling out the form that we have shared with you. Please note that since we will prioritize English questions, we would like to request you to ask your questions in English. Today, in the last session of the symposium, we are honored to welcome Associate Professor Hasan Ayaz from the Drexel University School of Biomedical Engineering, Science and Health Systems with his presentation titled Neuroergonomics, Observing Brain at Work. Now I'm turning my sound and camera off and I yield the floor to you, Professor. Welcome, Associate Professor Hasan Ayaz from the Drexel University.
Thank you very much, Gülbin. Let me start sharing my screen for my presentation. Okay, can you see my screen?
Yes, Professor.
Okay, great. Good afternoon, everyone, and greetings from Philadelphia. So thank you for organizing this activity. I'm very happy to meet with you and discuss my research. Today, I will talk about an emerging new field that we call neuroergonomics and how we can access brain activity to inform our everyday tasks, design of new technologies, and some of our recent results. So before I start, here are my disclosures related to the concepts that I will discuss today. I have pending and granted patents, equity in multiple startups related to brain research and medical devices. Okay, so let's get started. Okay, so here is our topic, brain. It's a miraculous 1.5 kilogram spongy tissue, but it is the most complex machine in the known universe. So as you know, it contains more than 80 billion neurons and trillions of connections between them that are constantly reconfiguring itself. And each brain has the same fundamental architecture, but it has unique characteristics like our faces. And with our lifelong experiences, there's a cumulative effect that changes our brain. So each of you are unique and special, and everything that you do, every decision you make, everything that you perceive and learn changes your brain. So this is a micro-etching artwork called Self-Reflected from neuroscientist and artist, Dr. Greg Dunn, and artist and applied physicist, Dr. Brian Edwards. So this Self-Reflected is on permanent display at the Franklin Institute. It's a world-class museum here in Philadelphia. And if you visit, I hope you can take a look at it. And Dr. Dunn explains the Self-Reflected aim is to focus on the nature of human consciousness and the connection between this microscopic brain and the microscopic behavior of the neurons. And in fact, there is tremendous amount of research focusing on the individual neurons, the genetics and the molecular makeup, and going further down into the details of the configuration and the architecture. But today, I would like to take you to the other direction, to look at the brain holistically and look at actually even multiple brains and the relationship and connections. So in the title, I said observing the brain in everyday life. So what that means? Actually, the typical brain research is done in artificial lab settings with limited tasks, and the participants even may not be able to move. And here, what I mean with everyday life settings is to be able to monitor the brain activity in complex and diverse environments and tasks. And it includes the typical work for specialized tasks, workers, warfighters, operators, pilots, surgeons, students performing different tasks, but also relaxing, resting, collaborating, playing, and in short, anything and everything that we do. So this is a big change from typical brain imaging settings, but if successful, it can provide incredible amount of information about the brain and how to improve us or the tools that we use, and also how to diagnose, treat, and even prognose neurological and psychiatric conditions. So this is a huge research direction, and we have a lot to go. But let me give you a more specific example of one dimension, like neurorehabilitation. So there is a growing role of functional neuroimaging to help guide the rehabilitation process, and so that we can see greater benefits to patients and maintenance of those gains over time. Functional neuroimaging can also provide individualized and targeted procedures as opposed to generalized approaches. And there are emerging new other modalities like virtual reality and neurostimulation to help with this process. For example, after a traumatic brain injury or stroke, there is a reorganization of these brain networks and activity changes that precede the behavioral performance of the rehabilitation task that needs to be monitored and assessed for better and more optimized intervention. However, we need a better understanding of these task-induced changes of the brain. First of all, even in the healthy brain, we don't have the full grasp of these changes. So we need to have better assessment of these, even continuously on an individual at a scalable approach. So why this is important? So we have a lot of understanding of the structure of the brain with these traditional neuroimaging tools. We can assess the architecture of the connections and the anatomical layout within the brain. And also related to that is the resting state brain networks. That is looking at the brain activity of an individual without any particular task. And we can understand various aspects like default mode network and other kind of typical resting state intrinsic architecture of the brain. But these are far from the task state brain networks, because we have the structural and resting state functional imaging at great understanding with the traditional neuroimaging methods. They actually lack the ability to measure the brain during an active task, and especially gross motor movements, more realistic tasks that are typically conducive to our everyday operations. So there is an unmet need to better understand this missing gap. So specifically, the traditional neuroimaging tools are not capable of capturing this information. So we need new tools that are wearable, mobile, so that we can capture the brain activity while individuals are actively engaged with these tasks. And this is where neuroergonomics come into play. So neuroergonomics is at the intersection of diverse disciplines: human factors, neuroscience, engineering, psychology, philosophy, and it originates from the use of scientific thinking in the design of tools, technologies, and environments. And neuroergonomics represents actually the next frontier for brain-in-the-loop systems. And it builds on innovations from all these human factors, cognitive engineering, and neuroscience research, starting within the second half of the last decade. And now it emerged as a new field to enable research to feel the gap for better understanding the brain related to everyday contexts. So maybe I should go a little back to talk about these trends, how these emergence of computers set the stage for understanding these technological developments. So here are the humble beginnings of actually the first digital computer that was built actually here in Philadelphia, not far from where my lab is, like 5 minutes walking distance. And this was originally announced in 1946. It's called the Electronic Numerical Integrator and Computer, ENIAC. It was a general purpose computer, the first of its kind. And it was heralded as the amazing machine that applies electronic speeds to the mathematical calculations at the time. And the machine shown here was room-sized. It took up the entire room and weighed 30 tons. And it used more than 18,000 vacuum tubes. And with all this machinery, it was able to count up to 5,000 in 1 second. It was amazing. But any other, computer, any other computational device that we have right now is much more powerful than ENIAC. But ENIAC started a whole new direction. And even by witnessing that limited machinery, Licklider understood its potential and he predicted a future of human-computer symbiosis. So like legendary von Neumann, Licklider saw similarities between the brain and the computer. They're both information processing units with memory, and they have actually a lot of complementary strengths. So Licklider envisioned that a tight coupling of these two would emerge with new capabilities. So today, computers are already an integral part of our daily life. Like we delegate our tasks. It's very few people actually remember phone numbers. We delegate all this memory storage and other information processing to our wearable computers like cell phones or laptops that we carry around us. And it's already they're part of our life. But this was predicted very early on when these machines were almost room-sized. So going forward, actually, it's not far-fetched to imagine a future where neuroimaging will be an integral part of our daily life. So that we will each carry neuroimaging units that will capture information from the brain to feed into a computational unit that will eventually help us improve our performance, do better with our tasks, or even help in clinical problems, diagnose or even prognose our clinical issues before even they turn into a problem or symptoms emerge. So that's kind of a future that we can go with the personalized medicine and using all these new tools. It's already starting. But let's take another step back and look at the brain and the cognition and how this is starting. So another giant actually is Professor Michael Posner, and he had many contributions into the neuroscience and human factors, but primarily he looked at the link between the brain activity and cognitive function. So he used in 1980s, 90s, very limited neuroimaging tools at the time, but he was able to understand a lot of key aspects of the brain mechanisms, like looking at the cognition, like high-level tasks like visual search, reading, and number processing. And there is a test actually now, like look at attentional shift, is now called by his name, Posner paradigm. And his work with positron emission tomography actually helped us understand a lot of aspects, also clinical information like schizophrenia and other mental issues. So after that, actually, one step forward, we can see Professor Raja Parasurman's work that actually connected the dots that using this brain information that we are learning, we have been learning, can be utilized in actual practical scenarios, in everything that we do, from driving a car to learning new skills. All these can be adapted. And when he proposed these ideas, like at the end of last century or beginning of this century, there wasn't any technology available to realize these. But now, after 2 decades, we are seeing that neuroergonomics is already full-fledged discipline with a lot of active studies, different dimensions with subdisciplines, and it's already generating practical value, and which I will discuss later if you have time. So where do we go from here? And I would say for the next step, the routine assessment is key. So wearables are already here. They're measuring the body and physiological signals for routine assessment, and the cost is going down significantly. But you might say all these wearable systems, they're extremely low cost, cheap, and they're low quality, very noisy. So how can we get any useful information out of them? But a recent study is actually a good example. It's part of All of Us NIH's program that aims to collect physiological data from 1 million people. And just in 2020, they published actually a study that showed data from 200,000 people using this Fitbit, extremely low cost, low quality, this noisy sensor data. And they actually showed that in the Journal of Lancet Digital Health, using these variable heart rate and sleep tracking devices, real-time flu prediction can be done at a large scale. So even with these noisy signals, extremely small portable wearable systems can actually generate useful, actionable information. And here's another example from Drexel University, my lab. And this is actually a novel device that we have developed with collaborators. And it can now do infrascanner, can do a task that was only possible with room-sized devices before. So infrascanner is a novel neurotechnology, and it transitioned from a research idea into an actual medical device that is now on the market. And it's already becoming the standard of care in some countries. It is the first portable battery-operated device to detect bleeding in the brain after a trauma, intracranial bleeding, and it's looking at subdural and epidural hematoma. And it's now a device that is safe, that can be used repeatedly to look at any delayed bleeding, and can be used anywhere from accident site to ambulances, emergency care to intensive care units. So I believe you will see many such new brain sensors that are extremely small, portable, and that can measure the brain in new ways. And this actually brings to the neuroergonomics. And neuroergonomics is the study of the brain, yes, but one may think, isn't that already done with typical neuroimaging and neuroscience research? And I would say conventional tools and approaches, yes, we can investigate the inner workings of the brain in extreme detail, but the problem is that this is done by assuming the brain is in isolation, like this one on the slide. However, our brain is never in isolation. inside an MR machine, we can only run artificial simplified tasks that are only focusing on the brain. That is far from what we do in real life. And the information that we will get is limited. For example, we cannot look at two people communicate, social cognition, or we cannot look at the brain in complex scenarios with different machinery, learning new skills from aviation to many other tasks. However, observing these is becoming more and more possible in real world, and this can only be done with variable brain imaging, like looking at brain-to-brain synchrony during successful communication between individuals and others, which we have done. So our body actually impacts our brain, and both are needed to understand the behavior. And all these three have not been incorporated together properly in prior research. Typically, one or two have been emphasized at the expense of the other. And what's unique about neuroergonomics is that we take into account holistically the brain, body, and behavior, and also include the environment in a continuum. And these are in fact tightly integrated, but it wasn't possible to look before. Like when you perform a cognitive task in a serene, relaxed environment, when you're resting on a beach, versus when you're in an emergency situation, you're looking at the task, how you engage with the same task is very different. So we need to take into account the environment to better understand how the brain works. It's a huge range from human to human communication to human automation interaction, and all these tools that we use. So the implications are immense. So here are the tools that we use in neuroergonomics research in my group. And we record the brain activity using EEG and FNIRS. And we can modulate the brain activity with the neurostimulation tools, TDCS and TMS. And actually, we have demonstrated some of multimodal approaches combining these neuroimaging and neurostimulation or different modalities together. But today, I will focus on particularly FNIRS and how we have incorporated different modalities together, like EEG and FNIRS, complementary measurements of the brain, or stimulation like TDCS and TMS simultaneously with FNIRS so that we can capture the impact of the stimulation. So if we quickly look at actually the evolution of FNIRS, we have seen a rapid change within the last 2 decades. At Drexel, we have been at the forefront of developing these technologies. So here we're seeing the evolution from typical traditional imaging settings to first wearable systems like typical room use, lab use systems. And from there to reach mobile neuroimaging, where we can take them into high fidelity realistic settings. But within the last 5 years or so, we can actually go to real settings, actual settings, like the cockpit of an aircraft and monitoring the brain activity of a pilot while he or she is flying the aircraft. And we have done all these studies, and we can actually not only record the brain activity, but we can decode the mental states in real time. So we can process and interpret the data while we're recording. So we can see that with the future neuroimaging, soon we will reach a state that we can continuously measure the brain activity over long periods of time. And so here are examples of studies from the last 1.5 decades in my lab that we have looked at a lot of brain mapping studies and compare with traditional neuroimaging earlier. And then later we started looking at more novel paradigms that is not possible to do with traditional neuroimaging. And we looked at different dimensions. We demonstrated the capabilities of encoding and decoding with classical paradigms and discrete cognitive, motor, and affective processes. So these are a few examples. And we have also integrated neuroimaging and neurostimulation to measure the brain activity in a loop. Here are a couple of examples, like a past PhD student, Adrian Curden. Here, a study looking at combining TMS and FNIRS, and we use the speed of processing task to accelerate the learning and adaptation by using the TMS in a strategic location that is identified by neuroimaging. And again, same approach we have done with different technologies with TDCS now, and a different task with spatial working memory, another past PhD student, Ryan McKendrick's work. And in this case, again, for that particular task, we identify the key brain areas with FNIRS and apply TDCS to those key brain areas. And we can see that in controlled studies where there is active stimulation and sham stimulation, we can see that the active stimulation, the performance is higher. So these are just examples of how to integrate the brain in the loop. And on the other side, I mentioned about the functional connectivity. Here's another example, again, past student Lin Chang, looking at the cortical connectivity, brain activity with functional connectivity to evaluate the transition period between the task modulation. And this is, we focused on the hand movement. And we are actually seeing the relationship of this motor-related mental tasks. These are typically used in brain-computer interfaces. And because motor imagery is very kind of relevant, we want to understand the actual motor movement. And we here looked at the transition period that a task modulates the brain activity compared to a rest period from this functional connectivity perspective. And we found that actually several increased functional connectivity periods during transition period, and specifically S1 and M1, and connecting to contralateral S1 and ipsilateral S1 and M1. And on another study here, again, my past PhD student, Alisa Batula, we looked at the difference and similarities between the brain activation patterns of actual motor movement versus just imagining that motor movement. That is the imagery. And here we are seeing the brain activity for different extremities, hand, left, right hand, both left hemisphere and right hemisphere. We're seeing a contralateral activity as we expect. And for the right hand, these are the foot and the right foot. And when we look at within a particular task, this is the motor imagery on the left two columns, and the motor execution on the last two columns. We can see this typical contralateral activity that we expect, which is much weaker and slightly dispersed on the motor imagery side. So we can actually now see the differences between the motor imagery, which was typically assumed to be the same as motor execution. So its amplitude and spatial activation pattern is different. So we can actually now use this to build better BCIs. And an example is, again, using this motor imagery information to collect this brain data and in real time translate that to control commands for a humanoid robot. And this was, again, Alisa's thesis. And another example is the neuroergonomic assessment of wheelchair. This was my past, again, MD PhD student, Sean Joshi. He actually just finished his thesis last June, and he's a dual degree program, both MD and PhD. So he's now doing his clinical rotations. But for the first part of his work, in this case, we did this assistive technology evaluation and wheelchair. And this was the first study where we look at various aspects of the wheelchair control during actual wheelchair driving. And this was done with colleagues in London. Sean actually got the Fulbright Fellowship to visit my collaborators over there, collect the data, and come back. And he later also got NIH Fellowship for this work to continue next steps. So in short, there is a lot of information that we can capture. So this was kind of getting the first study to analyze like how individuals kind of interact with these different tasks. And we manipulated the difficulty level, easy and complex environments. We look at the novice and experienced users. And we captured a lot of information about their behavior and relate the neural efficiency of using this task. And the information that we gain, again, can be used to design new types of wheelchairs eventually. All right, so another study that we looked at was developmental coordination disorder. And this is actually is a neurodevelopmental condition characterized by the deficits in acquiring and executing motor skills. It's typically in school children, and the diagnosis is really difficult. These children are often described as clumsy or awkward, but this leads to an impact on personal, social, and academic, and even occupational functioning later on. So, and there is a lack of neuroimaging with that particular condition. Here is like a quick summary of what we know, only a few studies, particularly because it's really difficult to do in fMRI. Functional studies, you can only look at very limited movement or imagery only. So we set out to do actually, again, with colleagues, a study where we look at this in actual movement for these children. More than 1,000 students were screened and only age 13 to 14. And I will not go into the details, but we selected two groups afterwards. And the experiment protocol involved both cognitive task and auditory stroke and motor movement and dual task scenario. Here is a snapshot of the active movement. And you can see the individual actually stepping up and down based on the instructions. This is the movement case. And then we can actually have the also the cognitive task, auditory stroke, with or without this. And we're looking at the prefrontal area. This is the main area that we're interested in. But in short, we were able to see that in the cognitive task, there is no difference. This is typically developing minus DCD. TD minus DCD, there is no difference in brain activity, but there is difference in the stepping task. And more importantly, more difference in the dual task, more demanding scenario. And in terms of neural efficiency, we identified also several places that the DCD has deficits in specifically in the dual task scenario. All right. Okay. So this is just a new paper, preprint that we actually submitted recently that is available, and the paper is under review in the journal, and it is the largest neuroimaging study so far, and it is also looking at active movement and include the cognitive tasks to look at the DCD, and we were able to identify key aspects that this is not a kind of inefficiency in the cognitive scenario, but it is in the motor control scenario. And it also can help access intervention earlier. And finally, we have a lot of studies focused on aviation, more than a decade of studies looking at using these measures to help improve the understanding of the operator state and the design of these complex tools. And like we had studies early on with air traffic controllers as they control radar equipment. Like you see here, some of the first studies, we look at longitudinally over multiple days, like 9 days, learning of new skills like control of virtual aircrafts. And here is a photo with me and my good colleague Frédéric Dohet in France, Toulouse. He has actually this nice aircraft in his lab where we integrated the neuroimaging in it, and we were able to collect actual data during the flight as well. And this is the decoding study that we published recently. And similarly, we have a lot of studies with human-to-human interaction. This is the speaker-listener coupling, where we look at the information transfer between a speaker and a listener. By monitoring their both brain activity, we can see the mental state changes. The brain patterns actually become similar because they go through similar mental states. And we have then multiple other studies looking at social cognition with a humanoid robot, as well as teams. Like right now, this is an ongoing study that we're looking at teamwork between multiple individuals in e-games as they play these games, cooperative games, and in the same room, in person or remotely. And we're looking at the impact of the experience and the background. Again, there are lots of other kind of studies, but maybe we can stop here, as we can see that the EEG and FNIRS actually can be used in natural settings. And we can look at the cognitive function with these tools. And not only in typical scenarios, but new emerging scenarios that are more in line with our everyday tasks. And we can use the information even at this stage to improve the design of complex machines. And we can monitor the brain activity longitudinally and look at learning adaptation and even potentially intervention kind of optimization. And we can develop like more futuristic side, implicit and explicit brain-computer interfaces with these techniques. All right, so I will stop here. Thank you for your attention. We recently had our neuroergonomics conference, actually. It was planned in Munich, Germany, but it actually was all carried out online. And our next conference will be this summer, 2022, this time planned in person in New York City. So hope you can join.
Thank you, Professor. I hope we can join too. Professor, I would like to thank you for this wonderful presentation. It was a pleasure to hear your work, and especially mobile devices excited me a lot. And now I would like to move on to the Q&A part, if that is okay with you.
Sure.
Our first question is, what are your insights about the future of neuroergonomics, since it is a rapidly developing field of research?
Mm-hmm. Excellent question. So we are seeing actually rapid development of neurotechnologies that fuel neuroergonomics research. So there are so many new types of devices that are coming up. And new, for example, ways of measuring the brain, like time domain FNIRS, that looks at the time of flight of individual photons from one light source to another in the brain, that we can capture actually absolute values of hemoglobin concentrations and new ways of capturing data. And all these new tools that are becoming more mobile actually will enable us to get more information from the brain. And that will in turn will help us better kind of mental state assessment, better for diagnostic measurements. And I'm expecting an improvement in our capabilities of extracting information from the brain overall.
Thank you for your answer. Our next question is, what are the opportunities in EEG-based neuroergonomics for 3D user interfaces?
Mm-hmm. Yes, I mean, the EEG is the the most popular wearable technology. I focused on fNIRS in this presentation. I didn't touch upon EEG, but the EEG's deployment is much larger than fNIRS. EEG and fNIRS are the two most popular wearable technologies, and they are still, EEG is is still evolving. We have seen a lot of new developments with the dry electrodes, with active electrodes concepts, and they are becoming more and more mobile, miniaturized. Now EEG amplifiers available commercially that are smaller than even a cell phone. And it can contain the battery. It can transmit the data wirelessly to a computer nearby. So they're already rapidly evolving. And it's exciting to see the potential. And we have various studies that I haven't mentioned today where we looked at merging the two, EEG and fNIRS, and they actually measure different aspects of the brain activity. I tend to kind of imagine that there are two cameras looking at the same theater seen from different angles. So they have shared information, but also they contain unique information, and we can actually combine the features from the two to have even higher classification accuracy for mental state decoding. Yeah.
Thank you so much. And our next question is, can neuroergonomics be used for flight safety or safe driving?
Mm-hmm. Absolutely. So we can use these technologies, first of all, to assess the driver's mental state, the readiness, situational awareness. So we can use these to see, for example, there's a saturation or overload in the pilot. Like Frederick has, some key work look at inattentional deafness. Like when there is a tunnel vision, when you are overloaded, you can't just get these new warnings, new alarms. So even though there are these new alarms, red lights ringing, if the pilot is oversaturated, overloaded, there is no way to process these. So we can now actually look at the brain activity of individuals in real time to assess this case, and then the system, like the aircraft, for example, instead of bringing in new stimuli, it can actually reduce the amount of information fed into the operator, shut down some different kind of aspects, some gauges, so that the operator or the pilot can have cognitive resources to engage with more important and relevant kind of information.
Thank you so much for answering our questions and this outstanding presentation. It was a great honor to host you in our symposium. And we would like to give you this certificate to express our gratitude.
Thank you, Gülbin. And I have to mention, actually, I am looking for postdoctoral fellows and PhD students in my lab. Multiple positions are available. If there are any interested students, they're welcome to contact me as well.
And thank you so much, Professor. Thank you for everything again. Hope to see you in New York and other research projects.
Thank you for organizing this activity.
Thank you, Professor.
And good luck with everything.
Thank you.